Right now, we are looking at a simulated urban environment, monitored entirely by a fixed passive overhead camera. The objective here is simple. When the camera's deep learning model detects a person loitering for too long, it flags them as suspicious. The mobile robot then needs to automatically navigate to that exact location to investigate. In early development, this is often handled by assigning the robot a hard-coded static map coordinate. The camera sees a person, and the code simply commands the robot to drive to a predefined XY waypoint. That works fine if a single actor always stops on the exact same mark. But in a dynamic environment, humans do not follow a script. If the person stops anywhere else, the system fails. The core problem is a language barrier. The overhead camera only sees the person as a collection of pixels on a two-dimensional screen. The robot's navigation stack, however, only understands spatial map coordinates measured in meters. When the system cannot translate pixel data into physical coordinates, the robot is functionally blind to the scene it is supposed to monitor. Let's view two robots side by side. On the left, the hard-coded system sends the robot to an empty, predefined coordinate, oblivious to the target. On the right, the path planner generates a precise route to the exact spot where the person is standing. How exactly is the perception node on the right dynamically calculating the target's map coordinates live from the camera feed? The engineering solution avoids expensive 3D depth sensors. Instead, it bridges a standard 2D camera with the 2D floor map using a mathematical tool known as a 3x3 homography matrix. Implementing this mathematical bridge transitions the robot from following a scripted path to responding to live environmental data. A homography is a 3x3 projection matrix. Think of it as a mathematical translator between two flat planes. The matrix takes any 2D pixel coordinate from the image and maps it to a real-world coordinate on the floor plane. Because it has 8 degrees of freedom, we cannot guess the values. The system requires baseline data to solve the equations. Specifically, the algorithm needs exactly 4 point pairs. These are 4 specific pixels on the screen where the corresponding real-world map coordinates are already known. Once those 4 pairs are provided, OpenCV utilizes an algorithm called ransack to automatically calculate the matrix and lock the perspective. The resulting homography provides a predictable mapping between the digital image and the physical floor, provided the 4 anchor points are accurate. To see how this works in software, we look at the perception node's boot sequence. A dedicated interactive calibration class pauses the vision software on the very first frame to establish the environment. The user manually clicks 4 distinct reference points on the floor, usually room corners or previously marked waypoints. For each clicked pixel, the developer is prompted in the terminal to manually type in the known physical X and Y map coordinates. To avoid repeating this manual process on every reboot, the resulting matrix is serialized and saved to a local JSON file. Next time, the software loads it instantly. A few seconds of human-guided calibration aligns the camera's perspective with the robot's global spatial awareness. This is a view of the real-time YOLO detection window, actively tracking a human target and calculating their position. Notice the cyan dot placed at the bottom center of the red bounding box. This point represents the foot. We must use the foot, not the head or the center of mass, because the homography matrix was calibrated strictly to the flat floor plane. Due to the overhead angle of the camera, tracking the person's head would introduce severe projective distortion, resulting in inaccurate map coordinates. Look at this cyan text labeled raw. Feeding that foot pixel through the matrix outputs a continuous decimal coordinate. Relying on these raw continuous numbers introduces a new problem. Micro fluctuations in the camera feed cause the coordinate to jitter frame by frame, which confuses the robot's path planner. To stabilize the target, we look at the yellow text labeled grid. The software utilizes a grid mapper class to generate a uniform half-meter grid across the entire map space. The system calculates the Euclidean distance from the raw coordinate and snaps it to the absolute nearest stable grid node. By isolating the foot position and forcing the data into a quantized grid, the system converts unstable, noisy pixel data into navigational commands. Even with a stable grid, we still have to manage mathematical edge cases. For instance, what happens when a person is detected at the extreme fringes of the camera lens? Because of extreme projective distortion near the edges, the matrix can mathematically generate a coordinate that exists far outside the walls of the simulated building. To prevent the robot from attempting to navigate through solid walls, the code includes an is-goal feasible failsafe. It checks every snapped coordinate against a predefined boundary box. If a coordinate falls out of bounds, the goal is instantly rejected and the system prints an infeasible goal warning to the terminal. Robust robotics engineering requires building failsafes that explicitly catch edge case math before it crashes the physical machine. This architecture replaces hard-coded coordinate variables with a dynamic processing loop inside the YOLO perception node. All previous coordinate dependencies have been removed from the script. Now, the image callback function actively computes this exact pixel-to-map-to-grid spatial data on every single video frame in real time. This closes the loop. Perception, spatial reasoning, and decision-making function entirely as a single, tightly coupled intelligence pipeline. By embedding a dynamic projection model into the vision pipeline, the robot gains the ability to locate and investigate targets anywhere in the scene, regardless of their starting position.